start with correcting some stuff from last time. Okay, so I'm on the previous lecture, page 1. So let's go line by line, because as I said, the colleague of yours made me attentive about a sign problem. This is okay. This is okay. This is okay. Yep. Yeah, it's okay. It's okay. It's okay. Okay, is this okay? So here is a sign problem. So I do f of x to be this guy, which is true. So let's do it like this. But then when I do the integral, I do it backwards, right? So I'm supposed to do integral x naught to x of f of s ds, yeah? And it's a problem with the sign because f is with plus and this is with minus. So to correct this and don't change whatever follows, what we're gonna do, we're gonna leave right. We're gonna leave this as it is, but we're gonna change this one to plus, right? Yep. Okay. And then f of x. Okay. So what's going on? So f of x is okay. So f of x will be with minus here. Okay. If you notice something, please let me know. Okay. It's with minus now. So now is good. Yeah. Yeah. Now it's correct. Good. So this is corrected. Yeah. So f of x is with minus. It was a minus problem. Yeah, good. And then another thing that he made me attentive is here, right? Because in the heat of the explanations, whoop, whoop, okay, I get this stuff bad. So this is E is less than, so it was what was written here wrong. So this is wrong. Okay, it's E less than EM. Obviously, okay. Then the level of energy goes to EM, and then you know here again, this is wrong, wrong. Ooh, okay. Is the other way around, is EM less than E less than 0. Yeah, that's what he was saying, which is correct what he was saying. Yeah, good. So that's corrected. So now the notes are clean. And so we go to what I prepared for you today. So I have 2 bits. So a part, you know, I wrote it already. So we're gonna go over it, and then, you know, at the end I have an example we'll do in detail. Okay. So there you go. Excuse me a second. I have people. Okay. Good. So last time we started to talk about this 1D second order damped systems. Okay, so the object of interest is to find a function such that it fulfills a certain ODE that models an elastic spring with a damping force in it. So how the model goes, well, we have a, this is, let's say, the elastic spring in its equilibrium position. So if I leave it here, it doesn't go anywhere. So let's call this 0, okay? And there's the OX axis, let's say. And then, you know, when we pull it out, it goes back by the restoring force, which is the elastic, you know, and it forms an oscillator, right? So it goes back, but this time we consider that there is a damping force basically opposing the motion, right? So if the velocity goes in the picture from right to left, right? So there's the velocity as it goes right to left, the damping will oppose that. So it will just try to slow it down. So that's why it looks like minus k times the velocity vector. And then the ODE that drives this or that models this system is something that is standard, let's say, in physics. So is this kind of ODE, second order ODE. It's a linear ODE in, right, X, the position of the spring. So as we discussed, you know, any second order ODE can be written as a first order system. In general, any nth order ODE can be written as a first order system with many equations, just introducing variables as the derivatives. But maybe we'll do this more a little bit later. Okay, so the total energy still exists in the system, and this the sum of kinetic plus potential, and is exactly as we did it before. So you'll just take it as math student, take it as a definition. I'm not asking you to guess what is the energy, okay? I'll just give it to you if we have to. The point is that this quantity, right, which we call the energy, is, if we wouldn't have damping, it would be conserved along the solutions, right? You know, we talked about this last time again. But in this case, because we have this damping, so there is energy lost in this damping, in this friction process, right? It goes into heat if you want, right? So the energy is not conserved, is lost somewhere. It goes into, you know, breaking the motion, right? You know, to this friction that doesn't allow the motion to go smoothly, right? So this, you know, appears mathematically, is expressed in the fact that the T, if we calculate it along any solution verifying this system 2, as I wrote it here, in this case, it won't be 0. So actually I computed, so when we do d dt along the, you know, the trajectories of the system, so we substitute, you know, these guys, so we do the chain rule and we do the right substitution, then we end up that d dt, right, the energy is decreasing in time and there is an energy loss provided this k is positive, right? So indeed there is a damping thing in there, which we expect. It makes sense, right? It makes sense physically. All right, so now also last time we talked a little bit about the solutions behavior, and I said you should study it from the book, but you know, I said, what about if I just do it, you know, just write it for you and explain it to you line by line. So basically this second order ODE is really like an ODE from your first ODE course. And how these were solved, we were building the characteristic equation, find the roots, and then depending on what kind of, if these roots were real or complex, we had different ways, you know, there were different solutions basically. So here, this is the solution written, the roots of that quadratic written in general, and now we have to consider cases. So the first case is when the roots are both real, and it just turns out that they're both negative. So I mentioned this last time that one can prove that they're negative for this kind of quadratic and this kind of roots. Okay, and then we write the solution in its full splendor, you know, the general solution where these constants C1 and C2 are determined by initial conditions. And we observe that if we take the limit as t is going to infinity, these guys, you know, the limit will always be 0. So I put here, you know, with gray, like, you know, like P1 would be -3 and P2 would be -2, and then take whatever constants you want. When you take the limit, it still goes to 0. So that's what I did there. And, you know, if we're drawing this, you know, it will look like this. So no matter where we start, we're going to end up in 0. So we're going to lay down, you know, at height 0 as t is going to infinity. In other words, the motion will die. The friction will stop the motion, of course, right? Again, you know, the physics is there, right? And this position where it stops, you know, nothing moves there, is called an equilibrium position. It doesn't go anywhere. So, you know, but this kind of behavior for the damp oscillator, it's called, you know, it says that the oscillator exhibits strong damping, okay? And if we're to do this picture, that's why I did this again, okay? In the phase plane, so we discussed about the phase plane, right? How would this look in the phase plane, this kind of behavior, okay? So first of all, what I drew here, okay, if you look at this picture in the middle, it's in 3D with X and Y. So X is the position, Y is the velocity, and T, right, the time is on the vertical. So we know that no matter where we start in this phase, down there, right, at T equals 0 in the horizontal plane, no matter where we start, here, 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 no matter, we're gonna line up and then converge, right, to X equals 0. So we're gonna end up lying down on this vertical right above the 0 point, right? So the solution for which X stays at 0 all the time, this is the equilibrium position, right? In my initial picture is, where is it? Is here, is this one that, you know, the poor oscillator is not pinched. It's not, it just sits there, right? It's a natural equilibrium. If I move it, it will start moving. And because of the damping, it will always go back to its natural equilibrium. And this is depicted in this funky picture I made last night. You have to admit that is a nice picture. I like it. Right? So all solutions, all roads go to Rome, right? All are lining up on X equals 0. Now, this is in space when T is, you know, on the vertical. But when I'm looking down on the XY plane, the phase plane, right? This is the phase plane. Okay, when I'm looking down, what do I see? Well, I see this red dot that corresponds to the 0, right? And the rest, I'm just taking their projections. It's a way of thinking, okay? And then I'm going to end up with these curves that represent there the phase curves. And to make sure that I understand where the solutions are going, I put these arrows that are marking the fact that, you know, as time goes, they're approaching this equilibrium solution. Now, I do want to emphasize one thing. When people look at the phase plane, they are tempted to say, oh, look at this violet solution. It ends in the equilibrium. It ends, yes, but asymptotically. This violet solution up here in the physical world never touches the equilibrium solution drawn in red. It's asymptotically going to it. And why it doesn't touch? Because if you have two solutions that have a point in common, because of the uniqueness of the solutions, they're the same. It's like you cannot have two different paths for the same trajectory. Or the other way around, if two solutions are bifurcating from the same initial point, it's like you have two different futures coming from the same initial condition. And this is not the world we're playing in this ODE classical mechanics, applied math, toyland, okay? If you want to have different futures, then I think we have to do something like stochastic calculus, maybe something else, right? But not differential equations done in this deterministic world, right? So, you know, if you have an initial condition, there is a future and only one. And this is mathematically ensured by the fact that the guys that are appearing in your ODEs, all those functions are nice enough. They're differentiable. They are, you know, we get into the existence and, you know, the qualities of the solutions of differential equations. And that's something that is done in a different course. But the world we're playing in these lectures is a world where, you know, you have an initial condition, you have just one and only one solution going through it. And that corresponds basically to having one initial condition, one future, okay? Not two futures. Or, you know, one position here, then, you know, I'm coming from the back from one trajectory that brought me here, not more, okay? So that's why when we do these drawings here in XYT plane, they cannot have a point in common, because a point in common between, let's say, this guy and this guy would mean that they are the same. They had two different pasts. No, that's not possible. Okay, they're different. So their projections will be different then. Okay, so we have to be careful. And then, you know, we have to put these arrows to mark, okay, in which way the solution evolves as time passes. So that's exactly what, oops, this arrows are marking, right? So they're, you know, if you want projections from the up. Okay, now, because all trajectories end up in the equilibrium, that's called a stable equilibrium or a sink or a stable node. It has different names, but it means the same thing. Then we have the case of critical damping, in which, you know, the roots of that characteristic equations are equal. Okay, they're both negative, again, you know, because k is given to be positive, and essentially is the same picture that we get as in the strongly damped case. So all trajectories will end up in the wonderful equilibrium. Okay, so there is some degeneracy in there, but essentially it goes the same. And this is the general solution of this equation as we did it in the ODE course, or you did it. You should have done it in the ODE course. Okay, that's what we did there. And finally, there is a weak damping case in which we have complex roots of the characteristic equation, right? So here they are, right? And to ease notation, I introduced this capital omega, right? So we can see how actually the roots look like. And then we write again the general equation as we know from the ODE course. Or we can see it as, you know, as an amplitude, right? And the phase, right? Like we discussed a little bit about how this can go into that one, you know, anyhow, that would have been a good exercise in the assignment. Too late now, maybe next one, right? So any combination cos sine can be written together as a cos, or could be written as an a sine, right? So it gets together, anyhow. So now what we're interested is what is happening with x of t as t goes to infinity. Well, this one again will line up to the zero solution, but it will oscillate. So to be honest, you know, here, the strongly damped case is the case in which you go, right, out of, let's say the equilibrium solution is here, okay? Yeah. So you go, you release it, and it just comes back, right? Whereas the weakly damping is the one that you go, you release it, and it does that, and it stops. So it has this oscillation with smaller and smaller amplitude, okay? That's the difference. How does it look in the phase plane? Again, you know, I'm going to think, oh, how does it look first, you know, in XYT? Oh, it goes, you know, like a spiral, because that's the formula of a spiral here, right? It's an envelope, and that ends up, you know, it like converges again to that zero solution in the middle, right? And then when I'm looking down, what do I see? I see a spiral going towards the center, right? So that's, again, a stable equilibrium, but it's a spiral, you know, it's called a stable spiral or a stable focus, okay? So these are like the ABCs of stability, okay? Actually, next time you're starting to study stability properly in 2x2 systems, okay? So this being said, right, the first thing that we have to do before starting to the stability of systems is study the existence of equilibria, okay? What are those and how do we find them, okay? So in general, right, so next lecture I'm saying here, we're gonna start to study the existence and stability in systems of this form, you know, so they're more general than what we're doing now, because right now what we're doing something like this. Okay, so they're kind of, so if you want here, I can put the y here, right? So they're a particular case of the general case of two equations to unknown systems. And then, once we study this, we have a bunch of applications that we can play with, from all kind of fields, right? So that will be fun to do. Until then, okay, first thing, let's define what is an equilibrium, right? So I always like to talk about an equilibrium as understanding it, in a very down-to-earth example. So yeah, you can think about that thing with the harmonic oscillator, the what we did, the damped oscillator. That's an example. Another one that I really like is with the in which we have a pot. Okay, so like a well. Okay, and then in here, let's say X, Y, Z, and then I have a little ping pong ball or a golf ball that if I release, right, and it stays, let's say it stays on the surface of this spot, it will go back and forth and back and forth, right, and maybe, if there is friction with the bottom, it will just stop, right, and then it will cool down at the bottom of the top. But if I take this ball and I put it down here initially, it will not go anywhere. So, it's what drives this ball to move? Oh, it's its weight. Let's just say that is a weight here, mg, right? And that's why it moves, because it tends to go down, right? But if I put it down, it will not go anywhere. So it will stay there forever. That's an equilibrium. It won't move, right? For all times. So if I'm extrapolating from this example, what would be an equilibrium for an ordinary differential equation system or an ordinary differential equation in any kind of space will be that solution in which everything is frozen, it just stays there, it doesn't go anywhere. So for this formalism that is here in system 3, an equilibrium is a solution x of t, y of t, for which x of t is a constant and y of t is a constant. Doesn't go anywhere. For my guy here, it will be x bottom and y bottom, whatever there in my drawing here, if you want to think about the drawing. Yeah. Okay, so now, if we understand conceptually what are the equilibria, how do we find them? Oh, there are solutions in which, for any time, they stay constants. So if they stay constant all the time, then what is happening? If x of t is xc, then this means that dx dt will be 0 for all t, right? So in other words, if you want, x dot is 0 for all t, right? But x dot is f of x and y, as I said there. So this means that f of x and y has to be 0. So that's for the first one, for this guy, right? And the same will be for the other one. Why did I put a 0 there? And I don't know. It's a y, yeah? Okay. So basically, we find them just solving the right-hand side of the system to be 0, right? Because the roots of these equations will be those positions in which x of t can and y of t can stay forever, can be frozen forever, and nothing will happen. The left-hand side will be 0 because it's a constant. The right-hand side will be 0 because it's a root of the right-hand side. Voila. Okay, that's exactly how they're found. And with this being said, I'm ready to start writing with you now, okay? An example, okay? So here, oh, I have an example. Why did I leave space? Okay, so let's do an example. So let's say find the equilibria of x dot equals x squared minus 1 plus y, and y dot equals x minus y. Okay, and because I'm inventing one. Let's put here 2y. Okay, yeah. So what are the equilibria? We'll do this a lot, okay? They are found by solving this, okay? So we end up with, okay, from where we end up to x squared minus 1 plus 2x is 0, and x is y, from where we end up that x minus 1 squared is 0 and x is y, from where we end up that x is 1 and y is 1. So the equilibria are x of t, y of t, x of t equals 1, let's say, and y of t is 1 for all t. Or people use this kind of right, the language, you know, they would say rather, they understand that the equilibria are solutions. So I don't have to say that there are solutions for which x of t is 1 for all t. They say the equilibria or the equilibrium points, right? They just put them as points, are x e equals 1, y e equals 1. And that's it. Okay, it's just, okay. Or we can write like this. There are various ways to write this. 1, 1. Okay. Maybe this is the most common way to see it. Right? This one here. Okay. There you go. Okay.
Professor?
So this that is finding equilibria.
Hello.
Yeah.
Professor?
Yeah.
I think that x squared minus 1 plus 2x is not the same as x minus 1 squared. Oh no.
No, 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 no. You're right. Yes. Sorry.
Okay.
And make it minus 1. Good. Thank you. Yeah. Good, good, good. Yeah. Good, someone is watching me. Okay. So it's a plus here as well. Yeah. Okay. So the point is that, you know, to find equilibria is to solve some equations. Okay. And as I said, next time we're going to start studying stability in general. Today, we're going to start studying stability in conservative systems with second order, okay? Because those ones, the stability for those ones is coming up from the phase space very easily. So I'm gonna write here, stability in 1D second order conservative systems. So it's basically stability in these guys, okay? And rather than writing the theory, I'll just work an example with you from A to Z, okay? So here. So let's say we have, here, I'm gonna write it first like this. Okay. So this is x dot is y and y dot is y dot is minus x squared minus 1. Okay. Good. So now I'm going to identify, right, that f of x is x squared minus 1, and I'm going to identify the potential. Okay, so that's one thing to do if you want one. So what would be v of x? V of x, so the potential up to a constant. So the constant, if you remember last time, not, you will remember, we just drop it, right? So this would be something like from x naught to x of f of s ds. So in this case is s squared minus 1 dx. So we end up with, so here I can write it will be s3 over 3 minus s in between x naught and s. Okay. So it's x3 over 3 minus x. And then minus x naught at 3 over 3 minus x naught. And this is the constant that we're gonna drop it. So basically, v of x is x at 3 over 3 minus x. So that's the potential. And then we have total energy, if you want, or the energy that we know it's conserved. We know it is an integral of motion, and I'm not going over that again. Okay. Is 1 over 2 y squared plus v of x, which is x at 3 over 3 minus x. So this is constant along any trajectory, and we're gonna call it E, yeah, like we did last time. And the first thing to do is to determine the range of x, or the regions of motion. And from there, we're going to deduce how to write or how to draw the phase space, although, we could use Maple directly, but, we'll just do it step by step to understand. And then, we're going to discuss about the equilibria. How do they show up there and where they are and what they do? So here, V of x is this. The system was this one. Okay. So what I will do, I will plot the regions of motion. Or if you want the range of x, that's another way of writing, of saying regions of motion is the same thing. So now I know how this function looks like because I did it before. Okay, so let's make it with green. So it looks something like this. Okay, and actually these are the roots, right? So what are these points? I'm going to do them in red. No, in green as well. Okay, so we do v of x equals 0, and we end up, oh, but I will need the space. Okay, so here under it, we're going to plot the phase space. So I'm going to make room for it, the phase space as well. Okay, so this is x, x, y. This is v of x. Okay, and then we have when v of x is 0, we get that x at 3 over 3 minus x is 0. So we end up with x equals 0, and x is plus minus root of 3, I think. Yeah. Okay. So these guys here, this is minus root 3, and this is root 3, and this is the 0. And now the equilibria for these systems, okay, this is equivalent, right? So for in general, right? So if we're doing x dot is y, y dot is minus f of x, right? This is y is 0 and f of x will be 0. But what is f of x, right? So f of x is the derivative of v, right? So in other words, the x equilibria, right? So the positions, whatever, are found at v prime of x equals 0. In other words, they are at the critical points of v, right? Well, long story short, in this case, you know, because it's, and that's how it will be in all your assignment, it's we just do the right hand side equals 0, right? So in this case, f of x is minus x squared plus 1. We don't have to do all this funky, okay? And then when we do it equals 0, we get x equals plus or minus 1. So I don't want to fill in the thing. So it will have minus 1 here and 1 here. Okay. And these are basically the critical points of the potential that give us the position of the equilibria. So in any case, you know, okay, I'll just leave it like this. Okay, fine. And I'll do them in red because they're equilibria. And now I'm gonna project them down. So this would be the equilibria in the phase space. Mm-hmm. I'm considering to redo the picture on the next page to have room to discuss the regions of motion and stuff. So you don't have to do anything. I'll just redo the picture here. Okay, and this would be the phase space. X, X, Y, and that was that. Huh? Or it was the other way around. Okay. So here they are. The critical points of the potential gives us the equilibria. And then we have these things where things are changing, but they're not important. Okay, so the first thing what I want to do with you is to talk about the range of x of regions of motion as the energy is increasing. And then we're going to discuss how we do the phase space and how we do the stability. So 2, right, because I said the 1 here, 1, identify the potential up to a constant and maybe the equilibria, but anyhow, okay. So 2, plot v of x. 3, okay, determine the range of x as function of E, okay? Or what I called regions of motion. And that's what we're going to do now. So we're going to start again with those levels of energy. Okay. So this point here, x is -1. What is y? Y is, not is -1, is 1, right? Okay. Is v in 1. So in this case is -1 and, why do I keep saying -1? So is -2/3, okay? All right, and this point here is x is -1 and v in -1. So it will be -1 and 4/3. Am I ready to release the analysis? I think so, yeah. So let's see. Okay, so now we're going to take a, this is going down. Yeah? Go down. All right, so if we take a level of energy that is lower than the most bottom of the thing, right? Remember, the regions of motion are determined by V of x has to be under the level of energy. That's the key, yeah? So we're going to have the following now. Let's say A. If E is less than -2/3, right? So that level there. So that would be E is -2/3, right? So if it's under, the only possibility for the energy to place is somewhere here, right? Because it has to be the dark green curve has to be under the horizontal corresponding to the level of energy, okay? So this is E is less than -2/3. Maybe I should do a different color. Okay, and that's the level of this kind of level, okay? And the light green is where I can be. So I can be only here, okay? So if I want to put this on the face plane, I will have here a starting point, if you want, or an edge point. And the only way I can go is this way. So in other words, this guy comes and goes. Okay, I'm not in a rush to put the arrow. The arrow, I'll put it at the end because I'll have where what, remember, for these systems, we have x dot equals y. If y is positive, x dot is positive, so x will be increasing. So the arrow here will be whatever curve I'll get, I'll have to put it in a way in which x is increasing. And then once I put an arrow, I put all of them because they all have to go to agree. You cannot have one going the other way with respect to the other one. Okay, so I will get there. When the energy is -2/3, okay, again, I'm going to put what I'm allowed to. So the dark green has to be lower than the level of energy. So I see my dark green here. Maybe I should do the dark green like really dark. Okay. There's the potential, huh? Okay. So I'm with the level at E -2/3. So I have to be with the dark green under it. Here it is, right? So I can be here and where else? Oh, I have a point here that I can pick up onto as well, right? So basically what I can do is here, I'll have again this kind of coming and going, but here I'll have a new kid in town, and that's a stationary point, that's an equilibrium. right? And actually, that's how we determined this -1 and 1 as equilibria, didn't we? There were equilibria. So we have equilibria. I'm going to put them here at, we have -1 and 0. Y is always 0 for these guys, and 1 and 0. Okay. So now, so if you want, I can even put this one as well, but I wanted to complete it as we go with the energy. And now I'm going to increase the energy again a little bit. So I have to pick a different color again here. I'll pick an orange one. So here is another level of energy, right? So this E is in between where it would change again. In 0, it doesn't change. It stays the same qualitatively. I'm going to make one like this, but you see qualitatively, it's still a dip on the right-hand side of the origin, and then it's a cut, right, on the left-hand side. So it doesn't change, essentially, is up to where it will change. It will change up here. But E is 4/3. So for E, now coming back to this thing, so for E in between 4/3, where it changes, and where did it come from? -2/3, right? So maybe I'll put it somewhere. So this E is in between -2/3, okay, and 4/3. Okay, so for any level there, let's see what happens. Okay, well, again, I have to be with the green curve under it, okay? Under the level of energy. The level of energy is with that yellow thingy, right? Yellow-orange. So under it, I'm here. So you see the dark green under the orangey, and here, right? So if I'm coming with the curve, again, I'm going to have something like whoop. And here, right, will be something like this. And I could make a color code. So I could put these guys with their proper color. So you'll know what levels do what. Here, ooh, right? Okay, and this fellow, I'll take it out and make it, what was that? Was a pinky. Make it a pinky. See? Okay. Now, this orange level stays up to E equals 4/3, right? So up to E equals 4/3, I'll still have, see, for this one, for instance, here, I'll have this one. Right? This kind of trajectory. And here it ends up here. So here. Okay. Okay. So for this guy here, the part that is the dark green is under, for this area, right? And that's what I'm taking down here. Right? Okay, so you see how the trajectory, of course, a different way to do this is to really plot the curves in the XY plane, because what we're getting here, the curves corresponding to the levels of energy. What we're plotting down here is nothing else but 1/2y² plus, what was the potential? X3/3 minus x equals E for different E's. That's exactly what we're plotting there. Okay, if you do an implicit plot in Maple, you're going to get this kind, and you're handy with it, okay? You're going to get exactly these curves. Okay, but I don't need maple for this. I just need to know how to plot the v of x, and then I'll just deduce them. Okay, so here we are at e equals 4/3 up there, and the same thing. Okay, so where am I allowed to play? Oh, I'm allowed to play here and here, and I have that point in the middle, that point. Okay, so let's do them with purple. Okay, so here is the purple, right? And then this guy will stop here. So it's something like this. More or less. Okay. Interesting. Huh? And then finally, we have one more level of energy that is above everything. So there's like high energy. Okay. All right. So what color should I do? Little blue. So here is E to be above everything. Okay. Well, of course, the potential keeps going up. It's not like it died. Yeah. All right. So what we're going to have, right? So I'm allowed to play in all these regions. So I can come from wherever I want to come from, infinity, minus infinity. But then, okay, I have a stop point here, right? As I'm coming down. So it's something like, ooh, okay. Yeah, that kind of. Okay. So, yeah, I knew that that will happen. Boom. Okay. Okay. There you go. And the red dots are the equilibria. Okay. And now I'm going to put the arrow, but the arrows, I already know how to put them because, you know, when y is positive, x is increasing. So here is my arrow. Okay. Sufficient to put one. The rest of them, as I said, they have to agree. So let's see if indeed is sufficient, or I might have to do some. So here it goes like this, this. Okay, the question is, what do I do on that side? Oh, I know, because they have to agree. Okay. If I don't know what to do, go back to, okay, so when y is positive, x is increasing. So on above y equals 0, all arrows have to go from left to right because x has to increase. That's it. Okay. And by the way, when you do this on your assignment, don't put 10,000 arrows, you know, couple would do. Each curve should have one arrow. Okay, that's the thing. But don't put for a curve 10 arrows. I know that they're there. Okay, you don't have to do that. Okay, all right. Okay, so yeah, now we have to write in words what we did. Okay, so so when E is less than 2/3, yeah, well, we have to kind of describe a little bit. Huh? So when E is less than 2/3, we got only this bit, right? So the trajectory, so x of t, it's just like this. Okay, so we're gonna just put the bounds. Okay, x of t belongs from minus infinity to an x mean that depends on E. Boom. B, when E is, actually we don't even need the and B, we'll just do it directly. So when E is in between, no, when E was 2/3 with minus, then x of t belongs from minus to infinity to an x mean that depends on E, and was that equilibrium right at +1. Okay. When E is in between now 4/3 and -2/3, then we have x of t is in between -infinity and x min of E. Or maybe we should put instead of union or in words. There we go. That's better. This level works better. Or x of t equals xc here, or x of t belongs to an x min of E to an xm of E, right? Others than the others, right? So as long as you understand what you're doing, usually, it's easy to write. So this was for the orangey one, right? So these are the orangey one. Okay, so maybe we should do a color code here. That would be the best, right? So I can do a color code and say x e of E. Not x0. Let's call it x0. And this was the xm of E, xm of E. Okay. And here is xm of E. And here is xm of E. And this would be x naught of E. You see what I mean? The blue one, right? This one would be an xm of E, right? The purple one, again, will have an xm of E, but they're not the same. So it's a color code, right? Different colors, different values, like in the picture. And this is -1, and this is 1, yeah? The red ones. Okay, and it keeps going. So if I'm a color, okay, let me be consistent then. Okay, so let's do the color. So this should be with pinky. And that would be an X max, actually, this X, because it's a max. Okay. And E at 2/3, right, is this one, and we did it with, what color was that one? I don't know what color was that one. This guy here. XM of E. Okay. I'll just leave it like this because I don't know what color is this one. Oh, it was a dark gray, isn't it? Yeah. Okay. So what is the morale of the why are we doing this? Okay, that would be the right question of you to ask. Okay, so why are we bothering with this? Okay, I'll tell you why. It is because, let's see where we started, right? So we started with this system, right? So I'm going to write it separately. Okay, so we started with x dot, or x2 dots, no, x dot was equals y. Y dot is minus x squared minus 1. We cannot solve this. That's why. We cannot solve it. This is not x of t is integral 0 to x of s squared minus 1 ds or whatever. No. No. Wrong. Wrong. Because I bet I'll see this if I put it on a test. Okay. We cannot solve it, guys. This is a second order system and we don't have a method to solve these systems. The only thing we can do is to give some initial conditions and do numerics. However, without solving it, I can tell you all possibilities that can happen in the system, all futures that are possible in the systems. And they're organized function of the level of energy. Okay, so for really low level of energy, I'll have only a certain type of trajectory that comes from infinity, approaches a maximum, and then goes back. Okay. Oh, by the way, talking about equilibria, right? So now we have to introduce two more notions about equilibria. So this red one is an equilibrium, as we know, right? But because the trajectories are staying around it, so the behavior near this x equals 1 equilibrium is exactly like what we did before with the harmonic oscillator. So it's exactly that behavior in which the trajectories are staying on a cylinder and they're just going up. So, yeah. Okay, something like that, right? Okay, so this is time, right? And this is x and y. And in down, what we see just these circles. And in the middle is the equilibrium. So that guy, that kind of equilibrium, so that's the equilibrium, right? And here are the, okay. So this kind of equilibrium will be called the center. Okay, it's a center. And you're gonna ask, is it stable or not? Some people say it's not really stable. I like to call it neutrally stable. Okay, and if we have time sometime, I'm going to tell you stories about this. Okay, all right. So the trajectories don't really go away, they stay around. Okay, so that's exactly how this x equals 1, right? So in our picture here, this busy picture, we have, where should I make room for it here? I'm gonna squish it in here. Okay, so we have 1 and 0 will be a center. Okay, and I'm asking you this in your assignment, classify the equilibria. Whereas the other one, okay, as we can see, you know, some trajectories come in, some are going out. Okay, how do I picture this? This is something like in a 3D. Oh, I actually prepared this. I don't know what I'm doing. Anyhow, okay, so in 3D, we will have the trajectories coming close and then going away. It's like, oh, you know, it's more like a tease. Okay, we can call them teasing trajectories. Okay, so if this is again time, okay, would be that kind of behavior that, you know, it's kind of coming, okay, okay, getting close, and then it's getting away. Okay, so it's coming and is going, and some of them, you know, will actually, we'll do this in more detail, is coming. Okay, so let's say this is coming like this, choop, and then again it's going away. So in this case, the equilibrium, which sits in the middle in red, right? So this is the wonderful equilibrium, okay, would be unstable. And these trajectories, you know, that are kind of having two directions that are coming and going. So it's coming this way and going the other way. Okay, so let's see. Okay. Okay, when middle sits the equilibrium, this is called, this is an unstable equilibrium. And its nature, you know, makes him to be called a saddle. Okay. It is called to be a saddle. So we're going to do this in more detail, but this saddle, we can already recognize them in the phase space of a conservative system. It's just coming. We don't have to do any calculation, okay? So when I'm going back to the picture, this guy here, right, I can put it here, -1 and 0, it's a unstable, okay, equilibrium. I could write it directly a saddle, okay, okay, and it's a unstable. So usually the standard questions are classify or stable and unstable and also tell me what it is. So there are two levels, is stable or unstable. And if it's stable, which kind of it is? Is neutrally stable, like a center? Is it, you know, a sink, you know? And then we'll have the unstable to be sources, but we don't have them in this kind of system. So in conservative systems, but you don't have to know this, but it's if you still work, if you keep working with them, they will appear naturally, right? There are only two types of equilibria that we can have. It's either centers or saddles, right? You cannot have sinks or sources because things have to be conserved. Anyhow, there is a more involved reason. Let's just put it like this. So once again, guys, why we're bothering with this? I'm going back to this example, right? We cannot solve it, okay? The only thing that we can do when we see this system is to open Maple or Mathematica or whatever you want and do numerics. But numerics is really unsatisfying because, you know, you can, you know, design trajectory, anyhow, draw trajectories or calculate them for a finite number of initial conditions, isn't it? So you're can take initial conditions x, y, x, 0, 0, 0, 1, 0, 5, -1, 0, whatever, you know, how many you want to play. How do you know that you covered all possible cases? Okay. So to answer a question, be my guest and try to solve it. We cannot solve this system because it's non-linear. There are no algorithms that exist to solve non-linear system. Okay, so there is no algorithm to solve x2 dots plus x squared minus 1 equals 0. There isn't. Okay, there is no recipe, right? So when you have something like right, you have a recipe for this, don't you? You have, oh, I'm going to do r squared minus 3 is 0 plus 3, so r is plus minus I with 3, and I'm writing the solutions. That's the recipe, right? So this the kind of recipe exists only for systems that are linear, where A is a matrix with numbers in it. Then we have recipes. For whatever it doesn't fit in this format, there is no recipe. There is no recipe, you have to invent stuff, right? And adapt. And I'm coming back to the thing, okay, so what do you do? Well, for low dimensional systems like this one, because it's just a 2x2 and actually it's one dimensional oscillator, well, okay, kind of, okay. But for two, you know, for, this is a 1 degree, anyhow, you know, coming from physics, let's just put it like this. Oh, you know, they discovered this way in which we can describe all possibilities that can occur when we're doing the integration when we're solving. We know what will happen. The motion is bounded or unbounded, and where does it go? And to be honest, you know, this is just the tip of the iceberg, because we could extract way more information from this kind of picture. You know, I'm not going into, oh, let's actually calculate what are these points, because we can calculate them. They're coming from intersections of this horizontal line with the potential, with the dark green one, right? So that's an algebraic equation. We can solve it, you know. But to look for a recipe that would tell us how to solve this kind of nonlinear, and why they're nonlinear, because we have quadratic terms, right? I mean, that's the distinction between linear and nonlinear. Whatever is linear in what applied math, modeling, engineering is doing, you know, we deal with it very well. And we deal with it very well because we have understood, and there are a lot of methods that work in linear spaces. When I'm saying linear spaces, I'm talking about Rn, okay? I'm talking about linear transformations, matrices. We know how to deal with matrices. We know how to bring them to change the coordinates. I'm coming back to that, right? In such a way that they become diagonal, right? And when they're diagonal, they, you know, things kind of start separating, you know, there are patterns emerging. But when you have nonlinear systems with this kind of stuff, no. So the best we can do is to say, oh, you know, maybe in the vicinity, you know, locally here, we're almost like in a linear space, and maybe we can deal with it like it's linear. Can we? The answer is yes. Most of the time, yes. You know, in place where we are, Toronto, right? You know, locally looks like a plane, but if you look at Toronto, you know, from outer space is a dot on a sphere or ellipsoid, right? Our universe is not linear at all, but locally, oh yeah, we're kind of living in a linear world, right? That's what it is. And you know, this is, as I come back to this example, it's just, you know, a tiny drop of what do you do when you really want to say something in general. Well, you adapt. And if we have time, maybe next time I'll tell you an interesting story about Poincaré and how he got, you know, a prize for dealing with nonlinear ODEs without solving a problem. So the prize was for solving a problem, like would be now, you know, $1 million to solve, I don't know, you know, some fluid mechanics. Actually, it is, you know, $1 million. I think it's still out there for this fluid mechanics PDs. So this was in 1800s, you know, anyhow. So it was this prize, and he won the prize, but he didn't solve the ODE. He just came with methods to study the nonlinear ODEs that just opened the gates to a really different perspective and understanding of what is going on. Something like this, if you want, but it's just a drop in this thing. So that's the thing. Okay, guys, 3:52. Time to go for a walk. Come on. Okay.